So thanks so much for inviting me. It's a pleasure to speak to you all. So my first slide is actually about where is Zucker Hillside Hospital, and by extension, Northwell Health. I'm actually affiliated with three different pieces of Northwell, and that's Zucker Hillside Hospital is the dedicated psychiatric hospital that's a part of Northwell Health. The Feinstein Institutes is the research producing grant receiving end. And the Donald and Zucker School of Medicine is the medical school that's affiliated here. And we're one of the largest health systems in the New York area. And this, as you see here, is the newer hospital that we have on premise here. And here at Northwell, just to introduce myself and my role a little bit, I'm trained as a psychiatrist. I'm a physician scientist, I guess, by background. I run a lab that is interested broadly in digital health and psychiatry, but really particularly focused on speech and language processing and natural language processing and using these tools to diagnose and understand psychiatric disorders, and with a particular focus on psychosis. I'm also a co-president of the Advancing Women in Science and Medicine group here, as well as the Digital Health Program, which is an initiative that's founded by John Kane, actually, to try to integrate our research interests as well as clinical interests in incorporating digital health and psychiatry. So I think probably very much on topic with several of your research interests. I just want to quickly introduce my team, of course, who are really necessary for all the work that's done here. Our research coordinators, both past and present, as well as postdocs, residents. Anil Malhotra and John Kane are some of the mentors that I've worked with here. And I also collaborate closely with the Linguistic Data Consortium at Penn. And Winterlight Labs, which is a startup company that does some work in this field and with whom we've done quite a bit of research. So these are some of my disclosures, just to put these out here for a second. And so I think that I'm not going to go very much into depth with the background here for the talk today, because I think that many of you are probably already aware and appreciative about how much automated speech and language analysis is a powerful and really scalable way to objectively capture information about mental processes. And the way that I often think about automated speech and language analysis is in terms of the domains of information that it's capable of capturing. So in terms of the information we extract primarily from audio, we can look at tempo and pauses in terms of speaking rate, pause frequency, latency, things like that. We can look at pitch and voice quality from acoustic characteristics. And then there are also NLP features which can automatically quantify aspects of speech, either relating to the content in terms of what is being said, what is the sentiment, what kinds of topics are they related to, as well as the organization and the delivery of how those things are being communicated. So we can look at whether it's simple measures like syntax and the presence of disfluencies, or we can use slightly more advanced NLP techniques, for example, looking at semantic coherence or also speech graph features to look at how speech is organized on a more discourse level. And so with all of these different avenues of obtaining information about speech, it's really, I think, a really promising way for us to investigate both these objective markers, which can help us produce better clinical tools for better diagnosis and whatnot, and also research tools for being able to perhaps parse some of the heterogeneity in disease, for example. So today we've done a lot of work. Like my lab, I think, is a bit spread out in terms of, we focus on NLP and psychosis especially, but we've kind of approached it from different perspectives kind of simultaneously. So today I selected these specific topics to go into in a little bit more depth. So we looked at the latent dimensions of speech disturbance from a clinical level, and then tried to relate these to automated speech and language features. We've looked at, we've gone into depth with large language models and tried to compare some of the features that can be derived from them and then in relation to the clinical dimensions of speech disturbance. And we've also used a multimodal approach with many different types of features to try to track changes in psychosis symptoms over time. So first, I'll talk a little bit about our work defining latent dimensions of speech disturbance. And this one is, I think, the only work that's already totally published and out there. The other works are still in preprint stages or in like submission stages. So this is more described in more detail in our schizophrenia bulletin paper if you're interested in looking at it later. The reason why we were looking at latent factors for speech and language disturbance is because in at least one of the important goals of computational research in this area is to try to objectively quantify speech-related changes in psychosis, right? But how should we define those clinical measures of interest? We can look at diagnosis on its own. So we can compare a lot of work out there, probably the bulk of work out there compares healthy controls to people with psychosis. But we also know that psychosis is in itself heterogeneous. The speech disturbances among people with psychosis can be very different from one person to another. So the thought was that perhaps if we're lumping everybody together, we might be like losing some signals in the noise. And we can on the other like end of the spectrum, we can try to model individual symptoms that we know are related to psychosis. So we can look at incoherence, for example, we can look at tangentiality. But the problem there that we encountered was that there was a lot of overlapping and co-occurring entities. So for example, does it really make sense for us to try to model tangentiality and circumstantiality like differently? Most medical students and probably like most residents and practicing physicians can't tell the difference between tangentiality and circumstantiality. So perhaps it's not fair to try to get NLP to do so. And we can certainly look directly from NLP features to clinical outcomes, which is also a viable option. But in this work, we wanted to identify latent factors or different dimensions of speech and language disturbance behind the clinical constructs, because we felt that this was a good like middle ground or a good like middle step, so that we can make sure that when we're trying to predict clinical outcomes, that there's some like ground truth validity to it and that we're picking up real things. And when we are a priori kind of like sub-objectives, or I guess like the things we wanted to achieve with this analysis is that we wanted to, of course, find latent factors that had statistical significance, but also clinical significance. And we were also we wanted to make sure that they actually had meaning for how we wanted to approach computational modeling as well. And because speech and language disturbances are often exist cross-diagnostically, we also wanted it to be valid for both a psychosis or schizophrenia specific population, as well as cross-diagnostically. So for this, by the way, I can't, when I'm sharing the screen, I can't see any of you. So if anybody has a question or a comment or something like that, just unmute and speak up. But otherwise, I'm just pretending that I see you. So for the approach for this project, we had a larger cross-diagnostic sample, and as a part of that, a schizophrenia spectrum subsample. And we first took clinical ratings for speech and language disturbances. Then we did an exploratory factor analysis. And then we did, on the statistical side, a confirmatory factor analysis, both in the larger cross-diagnostic sample and checking it also for the psychosis or the schizophrenia specific subsample. And then we related those factors that we derived to computational features in both samples as well, in the cross-diagnostic as well as the schizophrenia sample. And here are the participants that we had. We had healthy volunteers. We had people with other psychiatric disorders, which were people with like depression, anxiety, even substance abuse, ADHD, often comorbid with one another. We had people with definite schizophrenia spectrum disorders. So these were like confirmed either like high quality clinical diagnoses or a SCID-based diagnoses. And we also had some people with either other or undetermined psychoses. So these could have been people who had like bipolar disorder with psychosis, or there were people who had psychosis, but we weren't quite sure exactly which category they fell in. So it was like a less stringently characterized group. Let's see, I think, that's probably the main point here. Yes, and as you can see, there are some differences in terms of diagnostics, and some expected differences in terms of the global level of speech disturbance. So higher means more disturbance, and you can see as expected that they were, clinically speaking, people with psychosis had more disrupted speech than people with other psychiatric disorders. And for our clinical ratings, we used a combination of primarily the TLC. So that's the scale by Nancy Andreasen for the assessment of thought, language, and communication, as well as 2 items from the SANS, which we felt complemented the TLC. And I chose the TLC actually because it was the most granular scale, and it was also the most highly cited scale at the time. So out of those, we ended up retaining 14 items for the analysis because they occurred with enough frequency in our sample and could be rated relatively consistently with a ICC above 0.9. And we excluded a few items that just didn't happen enough for us to be sure that we were rating them consistently. And in terms of the factor analysis, there was a 2-factor solution as well as a 3-factor one. And I'll actually move ahead to this view of the same factor solutions, because I think it helps us see that for the 2-factor model, it was really kind of like it wasn't super interesting. It's kind of what you would expect. Like there's one factor that's kind of all the disorganized types of speech, and another factor that combined poverty of speech with decreased vocal inflections and increased latency. So that more kind of negative type of image. What I thought was really interesting, both from a clinical perspective and also from a computational modeling perspective, was when we looked at the 3-factor model, we got a split for the disorganized speech between what we ended up calling inefficient speech and incoherent speech. So the inefficient factor loaded highly was loaded on highly by tangentiality, as well as circumstantiality, pressured speech. So this is speech where like perhaps the individual units of speech at each sentence by sentence probably made sense, but they didn't make sense in with respect to the whole. So they weren't put together in a way that was efficient or relevant for the overall message of what was trying to be said, as opposed to incoherent speech, which related to incoherence itself. And I think a couple other solutions. So like neologisms, illogicality, where the actual like components of the speech, like even within a sentence or even within a concept, were broken down and were obscured. So first we did the confirmatory factor analysis, where for the cross-diagnostic sample, we got pretty good like fits for the 3-factor solution, looking at it 2 ways, either taking out cross-loaded items or with the cross-loaded items. And for the schizophrenia sample, we also got acceptable results for the 3-factor solution there. And those results were actually pretty comparable to previous factor solutions that were published in the literature. And really interestingly, I thought, there was a paper published almost simultaneously or just before our paper by a group in Germany. So they were using a different language, and this was also a large sample with something like 300 participants. And they were using the SANS and SAF scale, which is maybe a little similar to the TLC, but still different. And of course, a totally independent sample. But they actually found like highly convergent results with us, with a negative dimension, and then a separation between these more like these more macro level like disorganizations between sentences to the meaning of the whole versus like the coherence or the disorganization within these units of meaning. So that's our interim summary, that we found the solution with a good statistical fit and that these were convergent with very much independent findings. We also found that this distinction was clinically significant. So we found, whereas inefficient speech had a like noticeable intermediate effect, with people with other psychiatric disorders showing elevated inefficient speech compared to healthy volunteers, but less severe compared to people with psychosis. We found that for incoherent speech, it was relatively unique to psychosis. So people without psychosis had very little incoherence. And then impaired expressivity also showed a more intermediate effect. So that's the more negative, impoverished dimension. So next, we wanted to relate this clinical understanding to computational understanding. So we took open-ended interviews from these participants, processed separately the acoustics and the verbatim transcripts from those individuals, and generated some like many dozens of computational speech features. I think our pipeline in total puts out like hundreds and thousands of, not hundreds of thousands, but perhaps thousands of speech features now. But we chose some of the more meaningful and we felt like high yield ones. And we did a little bit of a statistical analysis to try to identify non-redundant features, and came up with 27 features corresponding to 9 categories for this analysis, just because having too much just confused the picture a little bit. So this is a pretty simple analysis, a correlation analysis, where we looked at the 3 different clinical dimensions and related them to the speech features. The point here was to see whether the clinical distinction between the 3 factors would have implications potentially from a modeling perspective. So should we be looking at them differently with different kinds of NLP and acoustic features? And the answer was basically yes. There was also differences among the different groups, by the way, which I think we should pay attention to. But we find that certainly impaired expressivity versus the disorganized factors were differently related to the objective features, but even the 2 different kinds of disorganized features were also differently related. And here's just the same thing, but with continuation of the other features. We plotted this similar kind of concept in a network type of way. So in the red, you have the 3 different factor scores, and then we demonstrated their correlations or illustrated their correlations with the other quantitative features here, so that you can kind of see how things group together or not. And you can see that they do indeed have unique relationships to the different NLP factors. So basically, so now we have these statistically viable understandings that where we're finding convergent validity, and we're also seeing that there's clinical relevance, with incoherence being more specific to psychosis. And now we're also showing that making this distinction is computationally relevant. So we should perhaps be trying to approach computational modeling of these different kinds of speech disturbances in different ways. So that's that particular project. And next, we dove more deeply into one particular NLP type of approach to look at these kinds of speech and language disturbances. I think many of you are probably already familiar with the ideas of word embeddings and looking at distances there. But just very briefly, I think for anyone who might not be aware, the concept of a word embedding, really, I think of it a little bit as like a numerical address for the semantic content, or like sort of the meaning behind a word. So here in the relatively simplistic example, you can imagine like providing numerical ratings for each of these different words along many different types of characteristics or different dimensions. And when we do this, if you were to plot or look at distances between the words, we get relationships that kind of make sense intuitively. So you might find that cat and kitten are the most closely related, while dog is, similar but a little bit farther away. And then all three of these might be farther away from the concept of houses. Or you might be able to reproduce relationships, like, for example, the trajectory or the vector from man to woman is recapitulates the one connecting king to queen. So this was I think a really interesting and foundational, word embeddings are a foundational part of how NLP works. And, it's been used, I think, to significant impact by, I think, BRiTE Elvevag's work back in 2007, which was one of the first examples of using NLP to look at thought disorder and schizophrenia. And then Cheryl Corcoran's also been using it to predict who among people with clinical high risk will eventually develop psychosis. So we were looking at the similar concept because we can we can kind of look at these word embeddings as a way of thinking about so-called coherence, right? Or what I actually prefer to call semantic similarity, because coherence is perhaps more higher level than the idea of similarity. And we also wanted to look more deeply into what large language models could potentially add to this type of analysis. So on this slide, it's just an example of one reason why large language models could be interesting in this context. So large language models are, models like GPT-3 and GPT-4 and BRiTE and many of the other ones that you might have already heard of. And they're different from traditional NLP in many different ways. But one of the ways in that they're different is that large language models can incorporate contextualized meanings to words. So in this example, while the glove, which is an older language model, said that there was no difference when we use the word, let's see, where's the word game? Oh yeah, so we have the chef put the game pie in the oven versus outside space aliens and astronauts loudly shouted game on. So it was not able to tell any difference between game pie and game on, or between tart desserts or apple tart in the toaster. But a large language model, by incorporating contextualized information, was able to tell these apart or to show distance between these different uses of the same word. So the reason why this is interesting for us from a clinical perspective is because many of the speech and language disturbances that we see in psychosis are pretty subtle. So there's a potential for large language models with this more sophisticated, instance of contextualized embeddings, that it might be able to give us more refined clues as to what's going on. So in this particular ongoing project, which seems to almost, it's like one of those asymptotic projects, which I feel like we're almost about to finish, but never quite. We tried to model these latent factors using semantic similarities with comparing large language models and also other more older traditional large language models, not large. And the analytical strategy that we took was modeled based off of a paper published by Alberto Parola et al., who this was like a part research paper, part meta-analysis or part review. And he summarized that there was the existing strategies that other researchers had used to look at semantic similarity. So we can look on the word level and look at K interword distances. So for example, a K2 interword distance, you could look at the embedding for Alex and then the embedding for the, and then find the cosine similarity between those embeddings. And then you would then next move to broke and vase and et cetera, et cetera. So we looked at from K1 to K10 for this kind of strategy, word level semantic similarity. You can also look at moving windows. So for example, if you looked at a moving window of length 5, you could take the first 5 words in this sentence and look at the pairwise cosine semantic similarity for all of those words, and then shift the window down by 1 and do the same thing again, and then average over all your results. And we can also look at utterance level semantic similarity. So when you have different utterances or which we approximate as sentences, you can look at first order coherence or similarity with adjacent sentences, or you can skip a sentence in the middle and look at second order coherence. So we took all of these different strategies. We combine them with 3 different levels of pre-processing to kind of see what the effects are there, looking at either verbatim transcripts, transcripts that were filtered of disfluencies, or also an analysis where we derived the embeddings from the no disfluencies pre-processing, but then filtered out embeddings only for the content words to compare. So that we called level 3 pre-processing. And then we did this with embeddings from several different language models. I think we added even more to this at this point. So the interim analyses that I'm showing you here are based on 98 participants with 37 people with schizophrenia spectrum disorders and 61 people who are healthy volunteers. And here we're looking at the relationships with the 3 different latent language factors that I talked about earlier. So looking at the different levels of cleaning, there's not that much difference, actually. We maybe expected a little bit more. If anything, we've been going with level 2 as the most logical choice. And we can see that first of all, that the different language models makes a difference. We chose these 3 language models here because they have different kinds of architectures. BRiTE is an encoder model. So some of you computer science people might know better than me, but this is an encoder-based model, whereas GPT is a decoder model, and T5 is an encoder-decoder model. And so that's why we chose these as our different large language models. And you can also see that for these, so these results are for the sentence level coherences, so comparing across those. And when we look across sentences, many of the effects are related to impaired expressivity. So that actually corresponds roughly to the clinical intuition I had, or we had when we were looking at the factor analyses, right? The idea that impaired expressivity was mostly describing clinical symptoms where it was the relationship between individual units and the whole discourse that was disrupted. And in contrast, here we're looking at effects from the word level comparisons. And when we look at the word level comparisons, actually there were more relationships with that incoherence factor instead. So again, maybe like matching a little bit our intuition that incoherence kind of clinical dimension was related to more granular, like lower level or smaller, or maybe more closer level changes and disruptions in the speech and language. So just to summarize, we're finding that LLM's utterance level similarities are associated with impaired expressivity also, as well as inefficiency, whereas word level similarities seem to be associated with incoherence, that more granular type of disorganization. We're finding that the degree of word level similarity is somewhat sensitive to the level of pre-processing used. So maybe something that we should be standardizing and paying attention to in our field. And also how we interact with the different language models may depend on the language model architectures, that the results we have do differ between models, and maybe is something we should pay attention to. So finally, the last piece of the story that I wanted to tell was how we can take these types of features, so including these kinds of semantic similarity features, but also like that a more of a greater range of all the other kinds of possibilities of how we can objectively quantify speech and language disturbances, and how we can use all of this together to relate to changes in psychosis symptoms over time. So these are results from a longitudinal study that is currently under review and being kicked around from paper to paper, unfortunately. So we call this LPOP, our Linguistic Predictors of Outcomes in Psychosis study. And our primary objective was to predict psychosis-related symptom trajectories, really, using speech and language biomarkers. And the clinical dimensions that we want to look at, instead of the three like speech-related dimensions I spoke to earlier, we focused more on like the clinically important dimensions of thought disorder, which is like kind of like disorganized symptoms, and versus negative symptoms versus positive symptoms. And the participants were all recruited when they were inpatients, so when they had acute psychotic or at least acute psychiatric exacerbations and were hospitalized. And this was a prospective longitudinal cohort study. We had 4 sessions in total. We enrolled people as close to the time of admission as possible. So as soon as they were first stabilized and it was safe and they were able to tolerate like a 1 or 2 hour long assessment. And then we assessed them again when they were stabilized for discharge. We did set like a 3-week limit on that, just in case, sometimes people stay in the hospital for a long time due to non-clinical factors, for example, housing-related factors. So it was either discharge or 3 weeks from the time of admission. And then we followed them up again at 3 months after discharge and at 6 months after discharge. The tasks that we used ranged from unstructured to structured language tasks. So on the unstructured side, we just kind of asked people like, tell me about yourself. How are you doing today? We asked people to describe pictures. So tell me what you see here. Tell me a story if you see one. And on the more structured side, we asked people to do category and letter fluencies. So give me all the numbers all the words that you know, starting with the letter F, or name all the animals that you can in 1 minute. And we also, on the most structured side, we had standardized paragraphs for them to read. So where we're focusing really on the acoustic signatures. And for the features, we had several hundred features, which I think I'll go into in a little bit, and representing these different kinds of categories. So a lot of what I was describing earlier, everything from timing to acoustic features to the content of speech to how it's being put together. These are the participants. Unfortunately, we did have a lot of dropout. This was done, a lot of the enrollment was during COVID, so we had like Delta and whatever came after Delta in the way at some point, and also like people's housing situations and living situations were very unstable after discharge sometimes. So unfortunately, we didn't get a lot of people at 3 months and 6 months. We did get 54 who had at least 2 time points for baseline and discharge. And kind of by design, they were fairly young. We mostly wanted to capture people with earlier phase disease because we thought that there would be more clinical change for us to pick up on. I think everything else is kind of the usual expected patterns. Here for diagnosis, they were mostly people with schizophrenia and schizophrenia spectrum disorders. There were a couple people who ended up having bipolar with psychosis. They came in with schizophrenia, but then on a skid, we found that they had actually bipolar just with psychosis. But we felt that it, came together enough from a dimensional perspective. And then in terms of the clinical symptoms, you see, I think, the clinically expected picture. So disorganized speech or thought disorder is decreasing over time. Positive symptoms are also significantly decreasing over time, but negative symptoms are staying more or less the same. I think that's what you pretty much expect from an inpatient psychiatric hospitalization experience. So to run this analysis, we first went through some pre-processing. So in total, that all those sessions, participants and time points added up to 160 sessions in total. We thought of the data as coming from 4 task categories. Oh, whoops. And for each of those task categories, we collapsed data, or we identified 317 of those speech and language features from all across those different kinds of categories, right? And so if you multiply 317 features by 4 tasks, you end up with 1,268 features and only, what was it, like 54, sort of 60, a couple dozen participants. So we ended up with what I think is a bit of a perennial problem in these types of NLP studies. I think almost always have way more potential features than we have participants so far. So the way that we dealt with this issue in this study was in the pre-processing step. So we first got rid of anything that was irrelevant for a given task. So for example, it doesn't make sense to look at semantic coherence for the paragraph reading task, right? Etc. So that got rid of a few features. Then we filtered out features that had very little variance. There was actually no features that were missing too much data. So that was great for our pipeline, I suppose. And I should say that this was one of the studies that was done in partnership with Winterlight Labs. We filtered out the features that were very high in kurtosis, so also describing data where there wasn't enough spread. And we then finally filtered out features that were intercorrelated with other features at R above 0.85. And there was some order to this madness, but I probably don't have too much time to go into great detail about that. But anyhow, we ended up with 357 individual features in our final feature set, which included all of these 44 acoustic and timing features, 58 describing lexical characteristics and sentiment, and et cetera, et cetera. So from these, we generated a single component using PCA just to be able to describe what does all of this language, speech and language information tell us in aggregate. And then we also picked out the top 50 loading features from that single component score to be able to get into nitty-gritties a little bit about what kinds of features are modeling what types of symptoms. All right. So I think this is like the last flow chart here. So for the first part of the analysis, we looked at the single component score, kind of describing this overall picture of speech and language features. And we compared them to the clinical outcomes of interest using linear mixed models. We looked at main linear interaction effects, main effects, linear interactions, and quadratic interactions. And then identify the best model to figure out the main model that we would be kind of considering. And when we did that, it turns out that the linear model for the single component score was the best performing in each of these cases for each of the different symptom dimensions. And so that's pictured here. So the way to read these graphs is that each of the individual points and lines represents an individual person, an individual participant, and their symptom trajectories over the follow-up period. And the colorful lines are contour lines for the single speech component. So basically, if you had a z-score of 0, so if you had an average single component for your speech and language features, then you were predicted to be here at baseline, here at discharge, 3 months and 6 months. And if you had very high values for your speech and language component score, then your symptoms were predicted to be higher at each of these time points. And on the other hand, on the other side, lower if you had very low values for the single component. And so on and so forth for these other graphs looking at negative symptoms and positive symptoms. And when the contour lines are far apart, it means that it's predicting greater variance in that symptom dimension at that time point versus when they're close together, which means that they can't really tell the difference. I think this is interesting, like showing definitely like a general relationship between speech and language and like changes in psychosis symptoms, which I think is a little bit new for the field. That's the summary there. But I think perhaps for people who are particularly interested in NLP, perhaps the more interesting part is when we started looking at the individual features. So here we took these were top 50 loading features from the single component score from an absolute value perspective, of course. And we took those features and looked at all the outcomes of interest. So we started out with the same outcomes as before: thought disorder, negative symptoms, and positive symptoms. It turns out that we didn't get any significant findings that survived multiple comparisons correction for positive symptoms. So then we hypothesized that perhaps positive symptoms was too heterogeneous of a clinical entity. And then we looked also separately at suspiciousness, hallucinations, and unusual thought content. And because the quadratic interaction model with time point didn't amount to much in our first analyses, we just looked at main effect and linear interaction, linear mixed models for these analyses with a p-value correction for the 50 different individual features. And then we report significant findings of p less than 0.05. So here were the individual symptoms there. Interestingly, thought disorder was related to subordinating conjunctions in several different related features. So subordinating conjunctions when we did a part of speech count, also subordinate clauses when we did like dependency parsing and whatnot. The other thing that you can notice is that like all the features are derived from picture and journaling tasks, but that's kind of fake. That's because the top 50 loading features were all from those because they had the most tasks. So that's actually kind of a biased effect because of the features that ended up being included. The other thing that's interesting was that thought disorder was related to some of these semantic distance type features using different, I think Google is BRiTE, as well as fast text language models. Let's see what else. And also to the number of like picture units identified. So to how many of the things in the actual picture the participant mentioned. And when we looked at negative symptoms, it was related to a little bit to this whole idea of subordinating clauses again, but also to like features like imageability, age of acquisition, things like that. And while we didn't get any individual features that survived corrections for positive symptoms in its entirety, we got several different significant relationships for suspiciousness, and some trend level relationships for hallucinations. Oh, and we got them for unusual thought content as well, but that was like very similar to the idea of, not for unusual thought content, for conceptual disorganization, but for unusual thought content, we did not get any specific individual features that were related. So these here for the graphs, we were just picking out and highlighting some of these individual features, looking at the relationships. Some of them had the linear interactions, but many of them, actually most of them, I don't know if you can see that here. So M stands for main effect here. So most of the features for thought disorder and for the positive symptoms were main effect models, so where the same degree of variance is predicted at each of the time points. Negative symptoms, all of the significant effects were linear interaction models. And I think that that's just because like from a practical, because negative symptoms are not well assessed in an inpatient setting, because you're on medications, there's medication side effects, and because often the positive symptoms and thought disorder are kind of just much greater in magnitude and obscuring potential negative symptoms that are underneath. So to me, it makes all the sense in the world that negative symptoms are best assessed when people are outpatient and not so great when you're inpatient. And here are some of those relationships for suspiciousness and hallucinations individually. And here I'm just putting them kind of side by side, looking at overlap and also like distinct relationships. So some features were related to just one symptom dimension here, while other ones were related to different symptom dimensions, but often in different ways. So I think orange means that it was positively related, and blue means that it was a negative main effect. So basically, so you can see that here especially. So I guess my conclusion there is that that we're able to potentially tease apart and be specific to different kinds of symptom dimensions using different speech and language features. And in general, thought disorder or so semantic coherence, imageability, and use of subordinate clauses really had cross-cutting significant relationships. Thought disorder was particularly related to those like subordinate clause structures and the ability to identify picture units. And negative symptoms were, after discharge particularly, were related to the use of modals and several features related to descriptive speech. And I think as a whole, there's probably more specific analysis, a more specific summary that I could have done, but I thought that overall, we can talk more about this, but I think that this avenue of research is very promising, and I'd love to see how it could help us achieve faster and more accurate diagnoses, preventative care in children and adolescents, and also give objective feedback, perhaps to guide medication choices and titration, as well as to personalize recommendations to optimize outcomes. And I think that's it.